Good afternoon. Good afternoon, ladies and gentlemen. I'm Ben Polak. I'm the Provost of Yale, and I'm the President of the Board of Directors of the Gruber Foundation. And it's my pleasure to welcome you here for the 2017 Cosmology Prize. This is the second Gruber Prize awarded here at Yale since the foundation became part of the university in 2011. So in just the past few years, the foundation has integrated into the university, furthering the excellence of both, and creating, among other things, the Gruber Science Fellowships, the most prestigious award offered by the Yale Graduate School to incoming students in the life sciences, cosmology, and astrophysics. And I know I think we have, some Gruber Science Fellows in the room today. If they're here, they can wave. Yeah, great, great. And we're very pleased that they're here. We're very proud to have them. We're very proud at Yale to be forming the next generation of groundbreaking scientists who will be poised to answer the world's most pressing questions. They start here as Gruber Science Fellows. Yale's faculty does leading work in exoplanet research, and the Express spectrometer, that's E-X-P-R-E-S, there's missing S because you have to say it very quickly, Express spectrometer, one of the most sensitive astrophysics detection devices ever made, was developed here at Yale in a Yale lab. At this fourth annual Cosmology Conference, we couldn't be more delighted by our collaboration with the Gruber Foundation and with the mutual benefit that it brings. I now present to you the co-founder and the president emeritus of the Gruber Foundation, Patricia Gruber, who will say more about the prize and the foundation.
Thank you, and thank you all for joining us. Welcome to the presentation of the 18th Annual Gruber Cosmology Prize, honoring a leading cosmologist, astronomer, astrophysicist, or scientific philosopher for theoretical, analytical, or conceptual discoveries leading to fundamental advances in the understanding of our universe. We are delighted to present the prize this year at the 4th Annual Cosmology Conference here at Yale on our home turf, where the foundation is administered. And we thank Ben Polak for his warm words of welcome. The Cosmology Prize was established first in the year 2000 as the first Gruber International Prize. And I'd like to acknowledge the founding vision of my late husband, Peter Gruber, in establishing these prizes, as well as his passing. Peter died in 2014 after leading a long and productive life. Born in Budapest and being Jewish, he fled Hungary with his family during World War II and settled in India, where as a child he was educated by Jesuits in the Himalayas. He became a Buddhist as well. As a young man, he later came to the US and eventually went to work on Wall Street. His success as an asset manager is what allowed us to start the foundation and its international prize program. To continue this legacy into the future, we reached an agreement in 2011 with Yale, establishing the foundation right here, where the science prizes and the human rights programs continue. Yale has hired our own Sarah Rea to guide the foundation, and I remain a lifetime trustee. The Cosmology Prize is presented annually in conjunction with the International Astronomical Union, whose support and partnership has guided our efforts since earliest days. It is my pleasure now to introduce its president, Sylvia Torres Pembert, who will say a few words about our long and fruitful collaboration.
Good afternoon. The International Astronomical Union is pleased to have collaborated with the Gruber Cosmology Prize since the prize was first established. The Union participates in the constitution of the selection advisory boards. The successive international advisory boards have carried out faithfully their mission in selecting extraordinary accomplished scientists as awardees. It would become very difficult to try to match the quality of the group that has now obtained this distinction. And today, of course, we have honored the most recent of the ones that have joined this group. In addition to the Gruber Prize, Cosmology Prize, part of our collaboration, as part of our collaboration, we receive an annual grant of $50,000 to be awarded to postdoctoral fellows from around the world so that they might pursue education and research at a center of excellence in their fields. The fellowship has been awarded to 19 young scientists from Algeria to Chile, covering all continents. On this occasion, the 2017 Gruber Fellow is Khaled Said of the University of Cape Town, whom I'm told that he couldn't attend and be here with us, but we are very pleased to have him as a fellow. And this,
Thank you, Dr. Faber. We are here today to honor the achievements of Sandra Faber. But first, let me tell you a little bit about the company she keeps with the other two prizes. The Foundation's prize program, which was started in the year 2000, offers 3 annual $500,000 prizes in the fields of cosmology, genetics, and neuroscience. Each prize recognizes achievements and discoveries that produce fundamental shifts in human knowledge and culture. The Genetics Prize was presented last week at Baylor College of Medicine to Stephen Ellis. In November, at the annual meeting of the Society for Neuroscience, the Neuroscience Prize will be awarded to Joshua Saines. Nominations for all Gruber Prizes are open till the middle of December. Returning to cosmology, we are proud of our entire illustrious laureate roster, and we're very pleased to be adding to it today. The 2017 prize recipient was selected by a very distinguished Cosmology Prize Advisory Board. We deeply appreciate the knowledge, the commitment, and the enthusiasm that the advisors bring to the entire judging process. Let me now invite the Advisory Board Chair, Robert Connecticut, to the podium to present the official citation and to let us know about the scientific achievements of today's recipient.
As you see, the prize comes physically with a very nice citation, which I'll begin, Sandy, by reading. The Gruber Foundation proudly presents the 2007, should I be on the one? Proudly presents the 2017 Cosmology Prize to Sandra Faber for her groundbreaking studies of the structure, dynamics, and the evolution of galaxies. Her research ranges from detailed studies of the stellar populations, masses, dark matter contents, and supermassive black holes in nearby galaxies, to surveys of distant galaxies over cosmic time. The results of these investigations have aided and inspired the work of astronomers and cosmologists worldwide. So that's the citation. But I'm not quite finished. One of the jobs that the advisory committee has is to draft these citations. And from the feedback I got in drafting it, we all agree, rarely has a citation more understated the achievements of its recipient. Of course, we're space limited with it. So let me give a slightly longer version and less formally. The problems that Sandy has devoted her career to, of course, have been a generational challenge to many of us, understanding the formation and the evolution of galaxies and the whole sequence. It has involved a large number of workers and has required breakthroughs in many areas: theory, observations. It's required new telescopes and instrumentation. And the cast of players, the physical players, the number of problems we have to address and solve is immense and challenging. And let me name a few. Dark matter between galaxies, dark matter in galaxies, the accretion of gas onto galaxies, the ejection of gas from galaxies, the conversion of gas into stars, the conversion of stars into gas, supermassive black holes, galaxies measured across cosmic time. Well, you get the idea. But what I want to know, in that list, comprehensive list, if you go through the literature over the last 3 or 4 decades, you will find papers with Sandy's names on them in every single one of those areas, starting when I said theory, and everything in between. And many of those papers, seminal contributions, foundational papers, and their subjects. So it's that impact primarily that we are recognizing with this award. The last thing I'll say is we tend to think of impact as measured in papers and citations, but I think it's also important to realize that impact is measured in people as well. And that takes me to the last sentence of the citation. Rarely, I think, has an astronomer been more influential on her students, her postdocs, her collaborators, and her colleagues, and the incredibly impressive audience that we've assembled today to come help share this happy event, I think testifies to that. So I'm happily you'll have to hear I'm done with the flattering. And I'd ask at this point, Sandy, if you could come up and receive the award.
Well, this has been a fabulous day. I knew it would be good. I had no idea just how good. And there's something about the format of this ceremony, managed by the foundation and also by the Yaleys here, that has just struck the perfect chord with me. Not too big, not too small, not too long, not too short, just the right people saying all the right nice things about me. I can tell you I'm just having the time of my life, and I just wish we could have more prizes like this so that more people could enjoy the kind of day that I'm experiencing. So I'm going to start by thanking you all just for that. I also want to say some special words about the Gruber Foundation. The Gruber Foundation, that name, of course, is legendary among astronomers precisely because of this prize and because the taste in previous awardees has been so phenomenally good. But I didn't really know that much about the foundation. I didn't know about Patricia and Peter before I came and did a little homework and talked to Patricia this morning. And I asked her, well, why cosmology amongst the 3 fields? And she said, well, we thought that somehow it really could contribute meaningfully to the well-being of humankind in a very special way. And in fact, she even used the word science philosophy. They haven't awarded an award yet in that field. But I think with cosmology, we're getting rather close. And now that I'm part of the Gruber family, I'm told once you're tapped, you never get a chance to leave. Maybe we could work harder on that, because I'm working on a speech that I'm to give at Berkeley in a couple of weeks on the importance of cosmological knowledge for the future of the human race. And I'm arguing, perhaps a little too enthusiastically, that cosmology will in the end prove to be the most important science for the destiny of humankind. So perhaps we can work on that theme, because I think I want to congratulate you on your selection of this field. I think it's on the right track, and maybe we can pursue that a bit more. Of course, then I have to thank the selection committee. I've been on committees like this. I know our field is so vibrant. There are so many choices. It's very, very hard to decide on a winner. You, Rob, has just been super nice to me with your kind remarks, and I'm very grateful to you and the rest of the committee. Thank you so much. I really feel, though, that this is a prize to many people. My career, maybe more than others, is kind of like an iceberg. There's some stuff that's visible above the waterline, but below there's this vast infrastructure of people, institutions, friends, and family that have really made that all possible. I'm going to say a few words directly to my friends and family who have come here today. Thank you so much. And this is the moment, I think, to acknowledge my husband, Andy, without whom none of this could ever have happened. And I'm reminded of a little anecdote when our kids were young and I was claiming that I was really never traveling that much. He challenged me and he said, look in your calendar for last year. How many of the nights were you away for dinner? It turned out that I was away 25% of the nights that year. And so Andy and I have definitely shared our family responsibilities equally. The next thing I want to talk about, though, is the other thing that's been so important for my career, and that is institutions. So I just went through and made this graphic pointing out all the institutions that have supported the work that I and my collaborators have been doing. I'll start here with the University of California. The University of California is a strange beast. If it could ever get its act together and really put the power of 10 campuses together in a concerted fashion, they like to brag about this, they say the power of 10. In fact, they never do that, with one exception, and that turns out to be astronomy. So the University of California has a great tradition. There was a little lapse of a few years that some of you know about. Recently, we fixed that. We seem to be back on track. They have been a cradle that has nurtured optical astronomy for over 130 years now. So from them spring Keck and Lick and the Demos spectrograph and the surveys that they created. That's sort of half of what I owe to institutions. The other half, of course, is NASA. And let me call out Jim Gunn, and a special thank you for that. He was the one who invited me onto the Wide Field Planetary Camera team, and that opened fantastic doors to me. What makes all of this possible, of course, though, are taxpayers. Taxpayers for the state of California and taxpayers who pay taxes to the federal government. And I have always been mindful that I am really working for the taxpayers and have taken numerous occasions to give popular talks and give back. So the taxpayers have to feel as though they've learned something important, and perhaps my talk on the importance of cosmology is just an argument to persuade them that in fact they have. I hope they have. In addition to institutions, though, as Rob mentioned, it's people. So I went through some of the major projects I had worked on, and I put here the people without whom this couldn't have happened. These are the people who have done all the work on my papers, and there are too many to mention in detail, but I do want to call out three in particular lifelong collaborators whom I've worked with for decades. David Koo, for having every idea in the world, and Joel Premack and Avishai Deckel for teaching me everything I know about cosmological theory. So I thank you three particularly, but everybody on this side for the privilege of working with you. Let me turn now to my talk. Taking the prerogative of the awardee, I changed my title. And what I'm going to do is I'm actually going to talk about a scenario for galaxy formation and quenching. Quenching means ceasing star formation, for those of you who are not astronomers. So this is a theory for how galaxies assemble their matter, make stars, and ultimately stop making stars. And my collaborators on this in particular are a wonderful young lady from China, David Koo, and many other folks. Let me start with a summary of what I'm going to say. So, the goal of this talk is to give a very big picture, a sketch, high-level sketch of galaxy formation and evolution. And I'm reviving a new, but actually an old paradigm, which many of our speakers talked about today, that galaxies evolve while they're star forming at the centers of relatively undisturbed dark matter halos. I'll say more about dark matter in just a second. Okay? And it's the premise of this talk that the halo properties imprint themselves on the galaxies, including their central black holes. Now, galaxies are quenching in this model when radiation from the central black hole goes out and heats surrounding gas in the dark halo and gets it hot enough that it cannot cool and fall in. And that's when star formation stops. The whole process of star formation and quenching is controlled by the halo, and halos seem to be a two-parameter family. Their mass and something else about them. I'm calling it parameter X. I don't know what X is at the moment. Anyway, two parameters. And galaxies, therefore, since they're created by halos, are also a two-parameter family. And these parameters are the stellar mass and the effective radius of the galaxy. Now, some of this sounds very familiar to people who've been working in this field, but let's work through it and see how there can be some changes and embellishments and maybe even improvements on what we've said to now. Okay, so again, for folks who are not familiar with galaxy formation, this is our working paradigm. We start out with a universe that's rather smooth in this stuff called dark matter, or sometimes cold dark matter, and mixed in it with it is ordinary matter. We call them baryons. That's the stuff of which this room is made, the baryons. And the point is that if we arrange some fluctuations in the dark matter in just the right way and let the universe expand, we have instabilities, gravitational instability occurring, and the peaks of the dark matter have a little bit of extra gravity and they draw in more matter. The valleys have less and they lose their matter to the peaks. And it's that process of peak building that makes galaxies. So this is a, well, that's interesting. How am I going to start this? You know, that I didn't think of. I will just skip, okay? So imagine that you were watching a movie. All of these particles are expanding. I'm glad I have only one movie. All of the particles are expanding because they're part of the expanding universe. All of these little weak blobs draw in more blobs, and you just see clusters of clusters of clusters colliding and merging to make one gigantic smooth halo. And that's supposed to be the dark matter halo of the Milky Way. And so, fortunately, here's a slide at the end of the movie. And we wind up with a rather smooth halo, but with lots of structure superimposed. And in the process, the ordinary matter has cooled and fallen into the center. Dark matter doesn't do that, making a central visible galaxy, which is where the stars form. And you see that the visible galaxy is much smaller than the halo as a whole. Okay, so that's the general, paradigm that we're working with. Okay, this is generally called the lambda CDM model for galaxy formation, and it could, in principle, be complicated. Why? Because we don't understand a lot of things about it. So, 3 main reasons. First of all, we don't really understand how stars form. We don't have a good theory for that. As Rob said, one of the things that stars do, and perhaps black holes, they instill feedback in the surrounding gas and perhaps drive gas out of the galaxy. We don't understand that, at least quantitatively. And then lastly, if you had watched the movie, you would have seen that there was a lot of colliding and merging of these little halos. And so mergers were thought to be an important part of the picture. So I'm going to argue to you that in fact, they aren't that important. But we didn't always know that. We had to take data, and one of the wonderful things I was involved in was this candles project. My co-PI, Harry Ferguson, actually was more important in running the project than I was. And why did we do this? We did this with the Hubble Space Telescope. Before candles, these were the pictures that we had from the existing camera. They were taken at blue wavelengths, and they didn't go very deep and they didn't show very substantial detail. Then we put in a new camera called WIFC-3, and it was sensitive at redder wavelengths. And because the universe is expanding, red light of distant galaxies, light is shifted to the red. And so this redder camera revealed all kinds of detail in more distant galaxies that we had not been able to see before. And so as a result of this camera, which went in operation in 2010, I think, we suddenly had a much more complete survey of galaxies in the universe out to within a few billion years of the Big Bang. So this was a great resource. And among other things you can see, you can measure the sizes of galaxies from these pictures. The radii are a big part of my story. Now, before the candle survey, this was a popular picture for galaxy formation. Major mergers are very frequent. They turn spirals into elliptical galaxies, and they create quasars by driving gas to the centers. This is a famous picture by Hopkins and Hernquist. Here are 2 spiral galaxies. They merge, they disturb one another. As a result of their interaction, gas is driven to the 2 centers, it feeds a black hole, quasar turns on, and you wind up with, in the end, after all of it is over, a rather regular looking object like an elliptical galaxy and a big black hole at the center. So we set out in candles to see if we could test this. There were a couple of predictions. If this picture was true, then AGN, that's what quasars are called, active galactic nuclei, a lot of them should look morphologically disturbed because they're created by mergers. In addition, these mergers would introduce some randomness and unpredictability. You see, we had gas-rich star-forming galaxies, and we wound up with a quenched galaxy here because of the feedback from the black hole that radiated. And that quenching process could occur really at any time in the history of the star-forming stage. And so therefore, you might think, if mergers were important, that the properties of these objects here would have some dispersion, depending on whether the quenching took place early or late. So that's another test. With its beautiful pictures, Candles was able to assess whether these AGN look disturbed. Here are 4 ways in which we judge that. And we had 2 samples, the AGN sample of the red triangles and a control sample which were not AGN, of the blue squares. And we found that they didn't look any different. So this was pretty strong evidence that mergers were not inevitable in creating AGNs. This is a big surprise. And then, using another technique, this is more theoretical. It's called halo abundance matching. I'll say more about it in a minute. It's possible to work out the progenitors of galaxies. Here's a Milky Way today. By doing appropriate arithmetic and counting, I can figure out what the progenitors of that Milky Way looked like. That's what this technique does. And our collaborator here, Aldo Rodriguez Puebla, has done the arithmetic and concluded that for the Milky Way, only 4% of the stars today came in from mergers, and all the rest of the stars were formed in situ within the Milky Way. So it's not as though there aren't mergers, it's just that they're not big and they're not that frequent. There are a lot of minor ones, but to first order, it's fair enough, at least that's what my toy model is going to assume, that these halos are relatively undisturbed. Okay, so enter this old paradigm that massive galaxies are mostly isolated during their star-forming phase, and each one sits at the center of a massive dark halo and grows in mass by a smooth accretion. So I spoke of this subhalo abundance matching technique. Actually, how does this work? It works because we have a very detailed and accurate theory for how the halos form. The halo physics is simple. You only need gravity. You can make very detailed simulations in the computer and wind up with a catalog of halos and how they merge and evolve versus time. Their numbers, their masses, and how they behave. So imagine you have that. We're looking at an epoch back in the past, and now we're going to look at the galaxy population at that time. And we're going to match up halos and galaxies. Here's the biggest halo in the catalog. Here's the biggest galaxy, stellar mass, in the catalog. Put them together. Okay. Next biggest, put them together. Okay? That's what's meant by cumulative here. Cumulative matching. So the upshot is that we put big galaxies into big halos and work our way down. This is an old idea. Here are a whole bunch of citations, and it's working progressively better and better and telling us a lot about galaxy progenitors. So one of the things, obviously, that it does, it matches halo mass with stellar mass. And this is the result from our colleague here, Aldo. This is a halo mass, this is a stellar mass, and this is a plot of how the stellar masses relate to the halo masses after you've gone through this procedure. And he's colored his results by redshift, which means time. This is today, this is back in time. And the point I'm making from this is that the relation is pretty narrow. It's not perfectly narrow, but it's pretty narrow. And the toy model that I'm going to describe to you is going to assume that it's perfectly narrow, that its 0 point doesn't change, and it's expressible by a power law over the important range, which is this range. Okay, so let's review the assumptions of this very, very simple halo-based model. Every dark halo is assumed to host a central galaxy. Bigger galaxies are in bigger halos. And here's the key point. Galaxy properties depend only on halo mass. Therefore, all galaxies of a given mass should look the same because they are all in the same mass halos, and halos are the only thing that matter. All right, well, let's now go out and test this. You need data, and as we've learned today, the data have been improving so hugely as a result of these candles pictures, and a partner, a sister project, PI'd by Peter Van Dockum here at Yale, called 3D-HST, which took prism spectra of many of the candles galaxies. And as a result of these two projects together, we now have these enormous data catalogs of redshifts, that's photo-Z's, colors, spectral properties, stellar masses, et cetera, et cetera. So this is new within the last 2 or 3 years. Now, with data like this, you can draw this diagram. It's called the UVJ diagram. And again, it was pioneered by Peter Van Dokkum and his collaborators. Very important diagram. This axis is how red a galaxy looks at blue wavelengths, and this axis is how red it looks at redder wavelengths. So you can see right away that there are two islands in this plot. And that's why this diagram was created in the first place. It was created to separate these quiescent galaxies from star forming. Quiescent and quenched are the same thing. Means no more star formation. So all you need is these three properties, U, V, and J magnitude, and you can sort galaxies according to whether they are quenched or star forming. But now we're learning more about the star forming part of the diagram. And we now know that this long axis is a measure of the amount of dust in a galaxy. Between the stars and the interstellar medium are these tiny dust grains. They're remarkably like cigarette smoke, about the same size. And when you look over light years, thousands of light years across a galaxy, even very tenuous smoke absorbs and reddens the light. And that's what is expressed here. These are reddened and these are much less dusty. And then it turns out also that the crosswise coordinate is also interesting. It tells you the rate at which galaxies are making stars when they are star forming. So if you're down here in this lower edge, you're relatively making stars very fast. And if you're up here, you're relatively making stars more slowly. So this diagram, in short, is a gold mine. From just three magnitudes, U, V, and J, you can learn a lot about galaxy evolution. Now, one of the problems of galaxy evolution and understanding it is the fact that you have to get your mind around a complicated process. You've got different masses you need to think about, and each mass is evolving in time along its own path. So visualizing this is a challenge, and we have found this layout to be useful. So take a plot, in this case a UVJ plot, and then divide the sample by mass, little mass, big mass, and also slice it up by time. Going back in time here is higher redshift. So this 3D grid allows you to plot three parameters in each one of these little grid squares, and you can just look and see how galaxies evolve. Now, how do you do that? You do that from this halo abundance matching technique I just told you, which is telling you what the progenitors look like. You're matching them up by mass. So, for example, the Milky Way today, which in some units has this mass, would evolve along this way, in this coordinate system, which is mass versus time. Galaxies are increasing in mass with time, and so, roughly speaking, things tend, crudely speaking, they tend to evolve along 45-degree lines in this diagram. All right, so now let's look at the UVJ data and think about whether or not it really looks like galaxies are only determined by their halo properties. Remember, as I told you, if halo is key, then every galaxy in a given halo mass should look the same. Well, it turns out that everybody in one of these squares has the same halo mass. And therefore, if the model were correct, we'd see one point there, or a little cloud of points. All galaxies would be the same. So we don't see that, we see a spread. Let's talk about that. The first thing that we see, by way of spread, is we see a spread in this direction for the star-forming galaxies. That, I have told you, is the amount of dust. And it looks, you'll have to take my word for it, looks like this isn't too serious. Some galaxies, when they're flattened rotating disks, can be seen face-on, and some are seen edge-on. And when you look edge-on, you look through a greater path length of dust, so the galaxy is redder. So most of this spread is just, can be chalked up to a geometric inclination effect, not serious. Okay, then, here's another thing. Amongst the star-forming galaxies, they're not all forming stars at the same rate. There's some scatter here, there are different colors. Again, I think we can argue that this is not too serious because it's reasonable to assume that galaxies, their star formation is fed by the rate at which they acquire mass falling into their halos. That's what fuels the star formation. And we know from dark matter halo simulations that that rate is variable. And furthermore, we even know that the amount of scatter that we see here in these colors and these rates is precisely very much equal to the kind of scatter that we would expect just because the infall rates are varying, fluctuating from time to time. So again, not fundamental. Now, the last problem, though, is a big problem. You will note that these are the quenched galaxies, these are the star-forming galaxies. There seems to be a big variation here in the star formation rate. Some galaxies have completely gone out, whereas these are still making stars, same here, right? So that's a problem because that's a very big difference that we can't just argue away in infall rates. It seems to be more fundamental. And so, if we accept that, some are quenched, some are not, this is not okay, we are now looking for a second parameter. So we now know that galaxies can't just depend on their halo masses, there's something else in the equation. So let's keep looking. So it's going to turn out in the toy model that this is the second parameter. But it's going to take me a little while to explain that. What's going on here? Well, let's concentrate on one of these panels. This is stellar mass, and this coordinate is the radius of the galaxy, r effective. And I want you to look just at the blue points. The toy model really describes only star-forming galaxies, not quenched galaxies. These are red galaxies not making stars anymore. Just look at the blue points. So in this absolutely wonderful paper by Vanderbilt back in 2014, he fit lines to the blue points. And it's really quite remarkable how regular they are. Okay, note how the slopes of the blue points are always the same, but the 0 point increases with time. In other words, the level here is going up with time. This is back in time, sort of crazy here. Here is now, this is long ago. You can see that the ridge line goes up. In other words, at a fixed mass here, galaxy radii are bigger now than they used to be. They are increasing. So that makes us think about radii in the halo model. I haven't spoken about them yet. What does the halo model say about radii? Well, it turns out that it has a lot to say about the average radius of an average star-forming galaxy. If you assume that average galaxy radii are always about 2% of the halo radii as a whole, you can explain 3 things. Okay? First of all, you can explain the instantaneous slope in those diagrams which I just showed you, 0.21 or thereabouts, that's predicted. You can explain the 0 point evolution of the radii versus time, this growth from then to now. And that means, if you think about it, that you have explained the average evolutionary path of the average star-forming galaxy in radius versus mass. And there are several papers that relate to this and are basically coming to this conclusion. So, let's go with that. And let's assume in the toy model the dark halo radii are setting the average RE of a star-forming galaxy. Okay, but we're not all the way there because we can see that there's scatter. All the radii are not the same. And this is now not allowed by the simple model, which depends only on mass. The radius scatter is going to turn out to be the key second parameter in the toy model. Before I introduce that, though, I'm going to take a little detour to set it up better for you and talk about another new galaxy structural parameter called sigma 1. And that's the central stellar density within 1 kiloparsec. A kiloparsec is about 3,000 light years. It's about 10% of the distance between us and the center of our galaxy. So it's not real small in the galaxy, but it's not half the light of anything like that. Small, but not too small. So here are data from the Sloan Digital Sky Survey, plotting this parameter, stellar surface density, sigma 1, versus stellar mass. This is in a paper by our graduate student, Jerome Fang, from some years ago at Santa Cruz. What we've done here is we've colored the points by their star formation rates. So the red sequence are the quenched galaxies, because quenched galaxies look red, and these are star-forming galaxies, often called the blue cloud. And the total extent of the quenched galaxies here is just about a factor of 10. And now we see, plotted in another way, exactly what we saw in the other diagram. At fixed mass, there's a range of galaxies here. They're not all alike. So this is another way of showing directly that quenching must come from some other property, not just halo mass or galaxy mass. And furthermore, it doesn't say that this parameter here causes quenching, but it's a good indicator. If you know both sigma 1 and m, you know where an object is in this plot, and you can predict much more accurately whether it's quenched or star-forming than you could if you only knew the mass. Now this is especially interesting. Many people today, in sort of parenthetical terms, express their belief that black holes have something to do with quenching. And that is inspired by this observation. It turns out, as we showed in the Fang paper, that for a great many fairly massive galaxies, this velocity dispersion correlates with sigma 1. Velocity dispersion to the fourth goes in proportion roughly to sigma 1 squared. Why is that important? Astronomers know because we have a well-known rule that the mass of a black hole goes as velocity dispersion to the fourth for many galaxies in which that's been measured. And so putting this all together, it says that sigma 1 is a predictor of black hole mass. So at the present time, we only know this for a handful of galaxies with all these measured properties, but the toy model is going to assume that it's always true. That it's true for all galaxies now, at all masses and back in time. So this seems to be an important diagram. Let us explore its evolution. Has it been with us forever, or is it of rather recent origin? That might tell us something about quenching. So we now see, thanks to candles, looking back in time, that this diagram is ancient. Basically, the same morphology is followed all the way back here to a redshift of 3, to within a few billion years of the Big Bang itself, making this one of the most constant and most ancient scaling laws that has been yet discovered for galaxies. So to summarize, this relation, sigma 1m star, is nearly the same at all redshifts except for a small decline in the 0 point. If you were able, I should have put this on the graph, okay? if you were able, you would see that these two 0 points are about 3/10 of a dex higher than these two 0 points. 3/10 of a dex is a factor of 2. It's not a big effect, but as we shall see, it's going to be absolutely crucial for the quenching properties of galaxies. So I'm going to call this the ridgeline, and I'm going to call this the ridgeline motion or ridgeline evolution. Okay, so another thing we know from these progenitor histories is that galaxies change their mass a lot between redshift 3 and now. The Milky Way, between redshift 3 and now, has changed by about a factor of 10. So, since this is a rather narrow locus, that tells us that the evolutionary paths of galaxies in this diagram must be more or less parallel to the blue cloud. So let's assume that. We don't know exactly what this locus looks like yet. We're going to find out in a minute. Let's just draw a line. Okay? This is a galaxy evolving. And we're going to posit, we're just going to assume for a while, that there's an invisible boundary in this diagram. And when the galaxy crosses over it, the star formation begins to go out. So a good name for that is the quenching boundary. And furthermore, we're going to assume that as the quenching ridgeline evolves as a function of time, coming down by 3/10 of the dex, that the quenching boundary will follow that. So both are moving, keeping pace with one another. All right, now back to radius. What does sigma 1 have to do with the radius of the galaxy? Well, it's easy to show. Let's make a plot of radius versus mass and color the points by sigma 1. A very obvious pattern emerges. Lines of constant sigma 1 are sloped here, and they have the same slope at all redshifts. In other words, the relationship between sigma 1, radius, and mass is really a plane in a three-dimensional space. Or another way of putting it is that the sigma 1 mass space and the radius mass space are basically the same thing, and a track in one is therefore, an evolutionary track, is therefore a track in the other. Lines of constant sigma 1 are diagonal here in this space, R and N. Okay, so now let's plot the track of an average galaxy. Remember a while ago I said we're going to assume that the radii of average star-forming galaxies come from the radius of the halo. Here's an average galaxy. It's evolving through this plane, and its slope and rate of evolution are now given by the rate and evolution of the halo, set by the dark halo, which determines both RE and M star of this galaxy. All right. We see that radii are not all the same. So here's a new assumption entering into the toy model. We're going to have different radii. They're all going to evolve on parallel tracks. That's an assumption. And the scatter here is going to be caused by something. I'm assuming in this talk that it's caused by something in the halo, and I'm calling that something parameter x. We don't know what x is, so just bear with me and assume that galaxies evolve like this. So here's the quenching boundary, which started out in sigma 1 mass, but it's the same space, so it maps over into this space. And when galaxies cross over that boundary, they stop making stars. Now, why is this physically reasonable? It's reasonable because of the physics of dark matter halos and their cooling properties, which have been contributed to by many people in this room. Here is a small halo filled with gas. Blue gas is cold. It's not pressure supported. It's falling onto its host galaxy and making stars. This is a bigger halo, 100 times more massive. It turns out that its temperatures are naturally hotter And at those hotter temperatures, it doesn't cool as effectively, and it can be pressure supported for a very long time, and it sits out there and it doesn't fall in. So if we had some way of converting the temperature of gas in halos to this higher level, we would have a quenching mechanism. That's what the toy model is assuming. Because as we evolve along here, sigma 1 is increasing, but remember sigma 1 predicts black hole mass, and so black hole mass is growing. And so the quenching power is growing as black hole mass grows. In other words, as objects evolve their way through this diagram towards the quenching boundary. Okay, so this is a big effect from the reasonable assumptions that we have made, hopefully reasonable. Going from here to here is a factor of 17 in black hole mass with the calibrations that we're using. This is the formula for black hole mass as a function of m star and effective radius. A byproduct here is that with all of these assumptions, it's just possible to read off the black hole masses in this diagram. You don't have to measure them, which again could be very useful. Now we already know this. We already know that black holes are bigger when galaxies are smaller. It's called the black hole fundamental plane, and there's a very nice paper on it by Remco van den Bosch a year or so ago. And here, this is not from his paper, it's from another one, but the idea is the same. Here's a plot of black hole mass versus galaxy mass. These are quenched galaxies, these are star forming, but it also turns out that these are small galaxies and these are big ones. So this bears out the statement that at fixed mass, the larger galaxies have smaller black holes. So again, trying to make it as plausible as possible that we should be able to predict black hole mass from sigma 1, I invite you to look at the Fine diagram, and specifically, just look at the portion of the diagram here that corresponds to this limit. And you can see that pretty much this morphology, red here, blue here, corresponds rather well to the morphology that you see in the Fang diagram. So, I have now introduced three spaces. Sigma 1 versus mass. I've told you that that maps on to effective radius versus mass. And the last point here is that in one more step, it maps on to black hole mass versus mass. So the assumption of the toy model is that all of these three spaces are the same, and an evolutionary track in one is a track in the others. Okay, so what does this do for us? Here's the quenching boundary. It's inclined because I mapped it from sigma 1 mass. And you can see now why it is inclined, because these galaxies have smaller black holes than those, and they have to evolve higher to get higher black holes in order to quench. So this inclination here of the quenching boundary reflects the fact that these objects here are relatively penalized compared to the smaller galaxies. Smaller galaxies start out with bigger black holes and will quench sooner. Okay, so let me pay an intellectual debt now to Peter van Dockum, whose paper got me thinking about how galaxies evolve in radius versus mass. And the picture of quenching that he put forward in this paper is really remarkably similar to what I've been saying. Parallel tracks coming to a quenching boundary, a boundary that evolves as a function of time, as the one I'm talking about does. And the only difference is that he assumed that the quenching boundary was given by a fixed value of the stellar velocity dispersion, and that would correspond to a fixed value of black hole mass. And we observe a wide range of black hole masses here amongst these galaxies, and so we know that that initial model can't quite be right, and we've just improved it here with a bit more physics for the quenching boundary. Okay, so here's a little movie just to stimulate your intuition. Here's a galaxy that will wind up, if it were unquenched, it would have a mass, law of mass of 10.6 today in a 12.1 halo. This is rather like the Milky Way. This is a small version of the Milky Way. So now, back in time, it gains in mass, it evolves along the track, the shape of which is set by the halo. And as it evolves, the quenching boundary is moving up in order to keep up with the observations of the ridgeline, which is moving. Okay, and you can see now that it's about to quench, and finally there it does. So I'd like to make 2 points here. First of all, the native evolution, once you solve all the parameters in the toy model, the native evolution of galaxies proves to be, that's the blue track, proves to be almost parallel to the quenching boundary. And it's the motion of the quenching boundary upwards that actually intercepts these tracks, kind of like a guillotine, and causes them to quench. Okay, and here's a set of galaxies, all of which started with the same mass at the same redshifts, but different black holes and different radii. Okay, I'm almost finished. Let me say a little bit more about the precise definition of the quenching boundary. So it is well known and assumed by astronomers that black holes do emit radiation when they accrete mass, and the total over their lifetime is proportional to their rest mass. This is black hole mass times c squared mc squared. And there's this number out in front which typically is taken to be about 10%, an efficiency factor. So if I see a black hole of mass MBH today, this is the amount of radiation that it might have, energy that it might have emitted in the process of forming. Now, let's do something with that energy. I've said that halo gas tends to be cold when the halos are small. But the black hole is growing, the gas is sitting out there, it's absorbing energy from the black hole. Let's write down an equation, purely empirically, equating the amount of energy coming out of the black hole with the amount of energy that the halo needs to absorb. And let's put an evolving 0 point into it. The evolving 0 point needs to evolve in order to fit the motion of the quenching ridgeline. And this parameter here is t, and we're fitting it to fit the observations. Okay, so k sub e and the exponent t to 2.0 are adjusted to fit the data. Saying a little bit more words about the unknowns in the model. There are 3 power laws. They have 3 exponents, s, v, and t. One exponent is known from abundance matching. This is the stellar mass halo relation. That's the power law I showed you in a graph a long time ago. This is the relationship between black holes and sigma 1, also assumed to be a power law. And this is the power law I just told you about. So we have 3 exponents and 1 evolving 0 point, and we have 3 properties, quantities that we can measure to determine those exponents, and we can match k of z to fit the 0 point that evolves. So the model is, there are no extra parameters, it's neither underdetermined nor overdetermined, it's exactly precisely determined. And these are the answers that come out, and the errors in these numbers are typically 2/10. Okay, so now you can predict where galaxies are going to lie in our T diagram. Here is sigma 1 versus stellar mass, and here is RE versus mass. These blue areas are the areas that are populated according to Vanderbilt, and these heavy red lines are the quenching boundaries, which we've assumed. And since the model is precisely determined, it's no wonder that we match the quenching boundary actually quite perfectly in all cases. And pointing out one more thing about this general diagram, these little tails show you the recent evolutionary direction of every galaxy and just drive home the point that galaxies tend to evolve parallel to the quenching boundary, and therefore it's the motion of the quenching boundary that's doing the main work of quenching. So it's instructive just to take a moment and look at the behavior of the energy coming from the black hole. Sorry, this is the energy needed to heat the halo, and this is the energy coming out of the black hole. Halos don't vary. They're one parameter, so they have a narrow relation. This scatter is due to the fact that at a given mass, we have galaxies of different radii and therefore different black hole masses. So, having chosen values of the exponent that fit the data, we see that the heat, the total heat coming out of the black hole is rising more rapidly than the quenching requirement of the halo. And when they cross, that's when the galaxy quenches. So at a given moment, here, this is today, these galaxies would still be star forming and those would all have quenched, reproducing the fact that at a given mass, at any given time, we have a mixture of quenched and star-forming galaxies. This is why. So, I stress again the downward curve of this E heat, which was adjusted empirically to match the evolving 0 point of the quenching boundary. And it's this downward curve with time that allows the individual black holes to overtake the halo. So you can think of quenching in this model as being a black hole eventually overcoming a progressively weakening halo. There are many major unknowns. I've talked for a long time. I put them in here if you want a copy of the talk. I'm not going to go through them, except to mention, again, that we don't know what parameter x is. I started out thinking that it was angular momentum of the halo, but now there seems to be accumulating evidence against that. There could be inner halo angular momentum. There could be angular momentum of the gas. There could be halo concentration, perhaps other things. And Arthur Jung and collaborators are working on this at this moment. And then there are other things. But let me now conclude. This is a deceptively simple little model. Just a bunch of little power laws and an evolving 0 point. And yet I think it has some refreshing and new and interesting insights. So, as I've said, galaxy quenching is not purely AGN quenching or halo quenching. Those two things have been discussed separately. It's a contest between the two, and the black hole eventually wins out over the halo. Halos become easier to quench with time. And by the way, from what we know about halos, that makes sense physically about them. The average radii of galaxies are assumed to track the radii of dark halos when those star forming. If you believe this model, it says that the same physics governs quenching at all redshifts, even out at redshift of 2, where some things tend to look a little different. Galaxies evolve nearly parallel to the boundary, and this is what produces a wide green valley. Remember I stressed that the green valley, the quenching path, is a whole dex wide. It's because those two power laws in the heat diagrams are so close to one another in slope. The angle is so acute that creates a very wide range of masses that are quenching. Galaxies almost do not quench. They quench mainly because the halos are easier to quench at late times. And finally, and this is really the essence of the picture, the halo and the central black hole evolve together. This is something we've wondered about for a long time. We think that black holes are important. We think that halos are important. Why is it that there seems to be, why does their combination seem so predictable? And in the toy model, this is explained because the halo knows about the black hole through the radius of the galaxy. Something about that halo predicts that radius variation, which in turn predicts the black hole variation, and speaking together, this is what produces a highly inclined, extensive, but narrow quenched ridgeline. So I return to the point that I made in the beginning, that the narrowness of the quenched ridgeline tells us a lot about the kind of physics we need in the model in order to predict that. And I think it was Rob who said the very same thing in his talk. Let me close by quoting your talk. Namely, if we don't really know the physics in detail, these scaling laws are surely giving us a big clue as to what we need from that physics. So why don't we adopt that, work with it, and see what we can do. Thank you.
Take a few questions.
Since it wasn't on your list of unknowns, because I didn't see it on there, what is your idea for what's creating the evolution of the ridgeline?
That's the K of Z term.
Yeah.
I think it's, as I've said, its evolution is consistent with what we know about the nature of halos. So consider a halo of a given mass at two different times. The evolution of the ridgeline comes from the fact that that mass halo at early times is harder to quench, needs a bigger black hole, produces a higher ridgeline than today. Am I on to your question?
Why is it harder to quench at earlier?
Okay, it's harder to quench. This actually is, Abishai has said this, people who do hydrodynamic models of halos have also found the same thing. It's basically because cold streams can more easily penetrate into halos of a given mass at earlier times. It has to do with the geometry of the stream relative to the characteristic mass of the halo that's quenching at that time. So streams are more diffuse these days and can't punch through the hot gas now as easily as they used to. There's that effect, and then there's the simple effect that a halo of a given mass is going to be less dense today than it was at earlier times. So put those two things together, and this at least has the right trend.
Two related questions. The first is your last point says why the halo knows about the black hole. I'm wondering if there's a reason that I missed that you're putting it that way as opposed to the black hole knows about the halo. And then the second.
I could have.
Okay.
Yes, it's a link. It's a link.
Okay.
They know about each other.
Okay.
Yeah.
And then the second question is about the evolution of halo radii. So this thing that you've posited about the size being proportional to halo radii, which on your crosstalk is up.
That's the average. As you know, at a given mass, the way we define radii, there's only one radius. So I can't appeal to fluctuations in radius at a fixed mass.
Right. But
I have to do something else.
that part, yeah.
Mhm.
So, but there is some debate in the community about, the definition of dark matter halos and what their radii mean and whether we're using the appropriate radius. And this could impact the evolution of time. So I just wonder
Yes.
if you thought about this.
I have thought about it, but I've not mastered the math
Okay.
and tried to do anything with it.
Okay.
Yeah.
Why do you think that it's not angular momentum? Because that is obviously something that very
know.
about from halos to halos.
I know. So angular momentum is the amount of spin that a halo has. And the baryonic material would naturally, early on, partake of the general spin of the halo. And if it's falling in with larger spin, it can't fall in as far. So larger angular momentum halos will make bigger galaxies. It's so natural. Maybe it's true, but people are not finding that it's true in hydrosimulations. And here I'm appealing mostly to my collaborators, Deckel and Premack and company, and they're looking at the hydrosimulations and not finding a particularly good correlation there.
Between the RE of the final galaxy and the spin.
Correct.
I'm not sure I thought this through correctly, but I have the impression that in this model, which I really like, by the way, the galaxy over a given stellar mass that is quenched has a smaller size. They live in the same halo though.
This model, to be very cagey with you, is only for star-forming galaxies and galaxies that are about to end star-forming.
Right.
It says nothing about the radii of quenched galaxies.
Good, because it's not where I was going.
Yes.
That there is now quite convincing evidence that at a given stellar mass, the quenched galaxies do live in more massive halos than the not quenched galaxies.
Yes.
And I'm wondering whether that is a problem for this picture or not.
I don't think so. I think I need to know more about exactly the statistic you're giving me. I mean, in general, galaxies don't quench until they come over here to high mass, and that's high halo mass. So in general, galaxies in small halos are not quenched, and galaxies in bigger halos are more quenched. Beyond that, I won't try to say anything specific until I understand your question better.
Well, let's thank and congratulate Sandra.
Thank you all.
Concludes our program. Thank you.